evening to everybody. Today we will take organic chemistry. In that some basic principles let us understand first. One of the topic is hybridization. This hybridization involves the structure of the molecule. If you want to know actually what type of bonds are there in the molecule, we have to understand. I will just take up the gist of the hybridization. In the hybridization, all the bonds which are between the carbon and carbon, carbon and hydrogen, single bonds between the CC and the CH, or the C oxygen or the C nitrogen, all such single bonds are nothing but the sigma bonds. These sigma bonds are formed due to the overlap of the hybrid orbitals, right? So these are all hybrid bonds therefore, okay, right. Similarly, there is a double bond between the carbon and the carbon. This is made up of with one sigma bond, that is original bond, plus one pi bond also. So wherever a double bond, if you see, it is made up of with the one sigma bond over that one pi bond. Similarly, a double bond nitrogen, a carbon double bond oxygen, and so on, they are all made up of with the originally one sigma bond over that one pi bond. If there is a triple bond like a carbon a carbon and nitrogen and so on, such bonds are made up of with one sigma plus two pi bonds, right. Now the shapes of the molecule is basically limited to this sigma bonds, not the pi bonds. How many sigma bonds it is making? Whenever carbon makes 4 sigma bonds, 4 sides 4 sigma bond, the hybridization is sp3 hybridization, right. Sp3 hybridization, its structure will be the 3 just like a tripod and a candle type structure. This is called what? That is tetrahedral structure. Tetrahedral structure. Whenever carbon makes only 3 sigma bonds, leave about the pi bonds. You need not to count the pi bonds, how many pi bonds are there. But if it makes 3 sigma bonds, generally there may be a charge on the carbon, or sometimes maybe a pi bond, one more pi bond will be there. But such a carbon will be sp2 hybridization, and wherein the carbon will have a 3 sides 3, the angle will be 120 degrees, and the shape of this carbon will be the trigonal planar. Trigonal planar. This is sp2. That means 1/3 S and the 2/3 will be P characters will be there in the hybridization. Whenever carbon makes only 2 sigma bonds, this is a sp hybridization, and the carbon will have a 2 sigma bonds opposite to each other. The bond angle will be 180 degrees. And obviously it is a line, therefore it is known as what? A linear structure. And this is angle is here 109 degrees 28 minutes. So these are the 3 types that carbon undergoes in 3 different varieties of molecules. Now let us go to a few questions which are asked in the previous this EAMCET examination, and after that I will give some questions which are predicted to our guest questions for the next coming years. Okay, the first question. In this question, which of the following statements is not correct? It is partly mixed actually with the concept of the benzene topic also, but however the question answer is here. See the answer 4, that is benzene has 2 carbon-carbon, that is has a carbon-carbon bond lengths 1.54 and 1.39. That is the benzene means here we have a the structure of the benzene is these are all 6 the carbons, every carbon is having the 1 hydrogen. So there are 6 sigma bonds are there, sigma bonds, 6 sigma bonds are internal, and 3 pi bonds are there. So answer goes to therefore. So there are 12 sigma bonds and 3 pi bonds are there. The sigma bond single bond is happens to be actually 1.54. The double bond should be 1.34. But here what is happening, all the 3 double bonds are going on shuffling. That is known as a phenomena called resonance. And as the result, what happens, the double bond and single bond lengths are mutually going on changing. So therefore, neither the 1.54 nor the 1.34, it will be in between around 1.39, the Armstrong units will be there. So it is an average length of double bond and single bond. So therefore, the fourth bit is wrong regarding this question. Next. A molecule X has 4 sigma bonds formed by the overlap of sp2 and s orbitals. 1 sigma bond formed by the sp2 orbitals, and the pi bond formed by the px pz orbitals. Which of this answer goes to? That is, it is an ethylene molecule wherein you find there are 5 sigma bonds are there, 4 sides, 4 hydrogens, and this is sigma bond, this is pi bond. So 1 pi bond between this. This sigma bond is sp2 overlapping. The other 4 sigma bonds are sp2 with the s orbital overlapping. So the description goes to the ethylene molecule. 4 hydrogens is ethylene. The fourth option is ethylene, right? So therefore, the answer goes to the ethylene molecule. Next. The number of sigma and pi bonds present in benzene respectively. Once again, this is the benzene molecule in which there are 6 hydrogens outside, 6 CC single bonds inside, 12 sigma bonds are there, 3 pi bonds are there. So therefore, answer goes to the fourth bit. Next. Which of the following columns, that is ethane, hybridization versus the different molecules were asked? Ethane goes to the sp3 hybridization, as ethylene contains 2 sp2 carbons, acetylene contains 2 sp hybridized carbons, benzene has 6 sp2 hybridized carbons. So answer goes to the first type, that is the answer. The pertaining question answers will be illustrated as a next. 2,3-dimethyl hexane contains. So here the hybridization, as a hybridization we are seeing, but actually the question is something, in name is given 2,3-dimethyl hexane, that is 6 carbons are there. At second carbon and at third carbon we have a 2 methyl groups. So therefore, 2,3-dimethyl hexane contains how many tertiary, secondary and primary carbon atoms respectively? Here whenever a carbon attached with 4 alkyl groups, this is called 4th degree carbon, quaternary carbon. A carbon containing only 3 sides alkyl groups, not the hydrogens, alkyl groups, then it is called tertiary carbon. A carbon containing the 2 alkyl groups, rest may be the hydrogens or some functional groups, then it is called 2 degree carbon. A carbon having the only 1 alkyl, rest may be the hydrogens and so on, but the alkyl groups are 1 only, then 1 degree. Or a carbon has no alkyl group is also taken as a 1 degree. So therefore, based on here there is no quaternary carbon, but there are 2 tertiary carbons are there, second and third carbons, and there are 2 secondary carbons are there. This is from this side, it is the 4th carbon, 5th carbon is secondary, rest of the all terminal carbons are the primary. So therefore, 2 and 4 is the answer, that is first bit is the right answer. Next. Which of the following hydrocarbons has least carbon-carbon bond length? So in the, as we have seen, there may be 3 types of bonds. Naturally, number of bonds increasing, bond length decreases. Number of forces attractions increases, bond length decreases. So whenever sp3 hybridization is, bond length will be long because it is sigma bond. Whenever sp2 hybridization, bond length is decreased. So therefore, here the least carbon-carbon bond you find in the acetylene, that is the 4th option is right. Next. The number of CC sigma bonds present in 1-butene. So first of all, we should know what is 1-butene. It is a 4 carbon containing compound containing a triple bond between the first and the second carbon, rest are the hydrogens. Now, this is the structure of the 1-butyne. If the triple bond is in between second and third, you should have say 2-butyne. Now, this is a 1-butyne. In the 1-butyne, how many sigma bonds, and asking his CC sigma bonds, that is, so here 2 and here 3, there are 3 sigma bonds are, therefore answer goes to the third bit. However, in the triple bond we have to take only 1 as a sigma bond, rest 2 are the pi bonds, we should not count. Next. Among the following compounds which have more than one type of hybridization for carbon atoms. So, this is the first bit, you see all are sp3 hybridization. In the second bit we have sp3 as well as sp2. In the third bit all are sp2 hybridization. In the fourth bit there is a triple bond was there, that is all are again sp hybridization. So, he asks which have more than one type, means here we have to go for the only the option 2, that is which contain terminal carbon sp3 and the middle carbon is sp2 hybrid. So, answer goes to the 2 therefore. Next. Benzene molecule contains a number of sigma and the pi bonds he was asking. Once again the repetition of the question here. The sigma bonds will be 12 are there and the pi bonds will be 3 and 12, answer goes to the 4. 3 sigma, 12 sigma and 3 pi. So, the hybridization involved in acetylene molecule. Acetylene means only the a carbon with the carbon triple bond with the 2 hydrogens. So, acetylene contains actually 1 sigma bond between CC and the other 2 are sigma bonds. Here hybridization is asked, therefore it is a very simple question. Triple bond, it is how many sigma bonds? As I said, count the sigma bonds, 2 sigma bonds are sp hybridization, right. Next. Number of pi bonds in the ethylene molecule. So, sigma bonds, number of sigma bonds in ethylene. In ethylene, a middle one 1 sigma and the 4 sides 4 sigma. So, therefore, it is a 5 sigma bonds are there, 1 pi bond is there. Answer is 2 therefore. What is the hybridization of middle carbon of the CH2C CH2? Now, this onwards, the previous questions, all the previous questions are they are already asked in the EAMCET question papers, different papers starting from the last 20 years we have collected. Now, this is the question, expected question, probably maybe here we have one small litigation also. People think that all the double bonded carbons are sp2 hybridized, but here the middle carbon has a 2 sigma bond this side, that side. So, that is the only 2 sigma. So, 2 sigma means here it is always sp hybridization, isn't it? 2 sigma means sp hybridization, 1 s orbital, 1 p orbital, overlapping gives sp hybridization, therefore, it is a sp hybridization. So, third bit is the right one. Next. The molecule or ion with sp2 hybridization, sp2 hybridization. So, the answer 4, that is a CH, that is a triple bond, CH triple bond Ca. I think it is not properly written. It is an acetylene with the carbon with the minus charge. I think this was the question here. With this question, the sp2 hybridization means this carbon has 1 sigma bond here, 1 pair. Always pairs also you have to include in the hybridization. It is not only the sigma bonds. As I said, 4 sigma is sp3, right. But here this is 1 sigma. 1 sigma cannot be hybridization. If there is another pair is there, this is also hybridized. So, according to this 1 sigma, 1 pair, that means 2 orbitals, hybrid orbitals are there. 2 hybrid orbitals are there, means it is sp hybridization, right. Methyl carbocation shows the following hybridization. Methyl carbocation means a carbon with the 3 hydrogens and the carbon has a plus charge. That is, 1 electron is missing. The available 3 electrons, 3 sides, it is undergoing with the sp2 hybridization. That is 3 electrons, 1 of S and the 2 of the P. So, it has got the trigonal planar symmetry, having 120 degrees planarity and all that, all the features of sp2 is right. Next. In a carbon dioxide, the first only the 1 carbon is there, bond is to second pi bond. First this side pi bond and the other pi bond was a bond with reference to the plane. So, the plane of the first C double bond and the plane of the second pi bond will be both are perpendicular to each other. That was the question actually. In oxygen, one plane will be there. The other side, because the carbon involves a pz and py, so these two planes will be perpendicular to each other. In addition to the sigma bonds, there are two pi bonds are there. These two pi bonds are perpendicular to each other. So, therefore, answer is a second. Next. So, there is a reaction known as this is a Reamer-Timer reaction or carbylamine reaction. In these both popular reactions, the CCl2, a molecule which is an attacking species, is prepared by the equation CH chloroform plus KOH gives KCl and H2O plus CCl2 with a lone pair. So, the carbon has two sigma bonds with the chlorines as well as a pair is there. So, how many sigma bonds? 2 plus pair. Pair is also hybridized. So, how many hybridized? 3 are hybridized. Therefore, hybridization is sp2 hybridization. This is a neutral species which will have a one vacant orbital and also a filled orbital. So, it acts as electrophile cum nucleophile, but in all these two reactions it is an electrophile. So, it is having the sp2 hybridization. Next. Which of the following is correct regarding the bond length between the second and third carbon atoms? See, this is a 1,3-butadiene, all the carbons are sp2, the last other side, this side, that side, the carbons are having the double bonds. In the middle one single bond is there, single bond happens to be a longer one. But the problem is here there is another concept called the resonance is involved. So, therefore, the bonds, double bonds will not be at a local stage. So, they are delocalized. So, therefore, all the three double bonds will have a equal length in fact. So, therefore, in fact, the middle single bond, the length will be slightly decreases. So, therefore, the question is here, between the second and third carbon bond, the single bond happens to be that less than the single bond length, that is the answer goes to the third. Which of the following have smallest bond angles? Smallest bond angles means sp3 hybridization will have a 109 degrees, as I said, sp2 will have 120, sp will have 180. So, the first carbon we have two triple bonds, therefore 180 degrees. The second molecule we have a sp2 hybridization 120. The third molecule all sp3 hybrid, therefore it is 109 degrees. In the fourth benzene it is again 120 degrees will be there. So, the answer goes to the 109 degree, that is sp3 hybrid containing third bit, that is N-butane. Next. The number of pi bonds actually, number of pi bonds present in benzene. There are sigma bonds asked, This is a benzene only, but here what happened, this is a structure proposed by not Kekulé, this is structure proposed by the Dewar. According to his theory, the two pi orbitals which are against to each other directly makes a pi bond. So, therefore, in the middle there is a pi bond is there. Okay. Just like benzene, this is also having the 12 sigma bonds and 3 pi bonds. The middle one is a pi bond, looks like a sigma. The other two are pi bonds. So, how many pi bonds are there? 3 pi bonds are there. As usually 6 hydrogens around the benzene, 6 sigma bonds. In between, that is in the cycle also made up of with the 6 sigma. So, therefore, 12 sigmas are there and 3 pi bonds are there. Here the answer is 12 sigma bonds is the answer. This is a subtopic in the basic principles of the organic chemistry known as nomenclature. This topic gives a methodology for the naming of the different organic compounds. Prior to this IUPAC system, there was some confusion in the nomenclature. So, therefore, once this international system has come, everybody is following this system. According to this system, there are certain rules are there we have to learn actually. The rule 1 goes to the longest chain rule, However, many internal points are there, but just I will explain. The rule 1 says longest chain. So, you have to select the longest chain and locate that mother chain and fix the root word, that is like hex or hept and so on. Rule 2 is a smallest number rule. Smallest number rule. So, after selecting the longest chain, you have to number from this end to that end or that end to this end. Middle start is not allowed. From the one of the end you give, so that the different groups gets a smaller number. That is the idea. Then you go for the reactivity order. According to this rule, when more functional groups are there, one of the most reactive group is identified as a functional group and it is coded, and the rest of the groups are prefixed and they are named. Alphabetical order. Alphabetical order. In this alphabetical order, if many groups are there, we are all prefixing them. According to this rule, we have to arrange them in the alphabetical order. Then, when more the similar groups are there, you can use di, tri, tetra and so on. Instead of saying methyl, you can say dimethyl. Number repetition. When the two groups are attached to the same carbon, you have to say 2,2-dimethyl instead of 2-methyl. The seventh rule is a branch with branch, sub-branch. Branch with branch. Whenever a branch has a sub-branch, then sub-branch is numbered and it is mentioned according to that within the brackets, and then it is attached to the branch and the whole name will be given. For example, if a compound is like this, main compound has a branch, that is ethyl group, it has a sub branch. Now, the sub branch is numbered from the attachment carbon, and this is mentioned at a fourth carbon. We have at fourth carbon we have a ethyl group. The ethyl is attached a methyl group. So, at 1 we have a methyl. The whole thing is on the ethyl. So, this ethyl with methyl attached at the fourth carbon of the heptane. So, this is the rule explains whenever a sub branch has got some branches. In the eighth rule, we have some punctuation. We have to use a comma between the two numbers. Whenever a number and word or word and number is coming, a small dash is used. When two words are coming, we have to join with them. Then let us see some examples on this particular issue next. So, the IUPAC name of the compound, the two CH3s are, one is up and one left, you right, and then goes to the a double bond, then a hydroxy group with a methyl. So, the answer goes to here, the first, that is 5-methyl. So, from the side of the OH we have given, not from the methyl side, because the OH is an important group. In the numbering we have that sub rule is there. Whenever a functional group is there, take care of that functional group, the totaling is not the necessary. So, according to that sub rule, we have to number from the hydroxy and say that is a 2-ol. It is a hexanol, having a ene also, therefore, it is a hex 3-ene 2-ol. The methyl is fixed at the fifth carbon, though from that side methyl is second, but we have given a preference to the OH, therefore, the answer 1 is right. Next. The structural formula of 2-methyl-2-butene. 2-methyl-2-butene means first you write the 2-butene first of all. This is called 2-butene, leaving the hydrogens, and it has got the 2-methyl. That means at second carbon we have a methyl. So, this is the 2-methyl-2-butene, and naturally the answer goes to the double bond in the center, means the answer goes to the fourth one. Next. The IUPAC name of the compound. This is a 1-butene containing a methyl on the 2. So, therefore, 2-methyl 1-butene it is. Okay. 1-butene, butene 1-ene or but 2-ene. These are all slightly differences are there, but numbering should be perfect. That is, the methyl on the second carbon is right. 2-methyl 1-butene or but 1-ene, that is answer 2 is right. The compound has a 6 carbons longest chain. It is a hex having a methyl on the third carbon. So, it can be from the fourth, from the right, left 3. So, therefore, 3 will be taken as a granted. So, 3-methyl hexane is the right answer. Answer goes to the third bit. Next, what is the word root used in the IUPAC name of this compound? Actually, in the nomenclature, there are very less questions are coming from the nomenclature. From the last, only the 4 questions are there from the last few years, and this is only an expected question which we have prepared. So, what is the word root or root word used in the IUPAC name of this following compound? In this compound, actually the OH, if you take on the carbon, that straight carbons, only 4 carbons are there, is a misleading. So, people may go for the but, but actually the longest chain which has got the OH also included, so which is a pent. So, therefore, answer goes to the 3. It is a 2-pentanol containing the 4-methyl. 4-methyl 2-pentanol is the right answer actually. Next, the IUPAC name of this, there are 2 carboxylic acids attached to a methyl group. We can go for the different nomenclature. Malonic acid is the right name, but not in according to the IUPAC common nomenclature. Methane dioic acid, methane as taken as the middle carbon, 2 oic acids are there, that is also a common method. Propane dioic acid, that is the right answer. Root word prop is taken, fixed ane as a single bonds. Then dioic acid, need not to mention 1,3 because oic acids will be in the last terminal carbons. So, the right answer is 3. So, this is an ester carboxylic acid attached with ethyl group. So, the ethyl is prefixed and then said it is a 1 carbon oic acid is called methane O8. So, the last answer ethyl methanoate is the right answer. However, some of the names like ethyl formate, third option is also right, but not according to the IUPAC. Systematically means it is IUPAC nomenclature. So, answer goes to the 4th only. There is a small problem in this compound. There are 3 chlorines are there, 2 carbons are main chain. So, from the left side if you number, it will be 1 1 1. But from the right side it is 2 2 2, which is better, means actually smaller numbers are better, but the carboxylic acid carbon will be given 1 and the rest of the 3 chlorines we are not bothering. So, therefore, 2 2 2, let the big sum comes, but the ethanoic acid first carbon is given a preference, therefore, it is the third answer is right. That is 2 2 2 trichloroethanoic acid is the right answer. It is a keto and aldehyde, 2 functional groups. Whenever 2 functional groups are there, we have to follow the reactivity order. In this reactivity order, a question can be reframed, which of the group is more reactive. In fact, aldehydes are more reactive than ketone. Therefore, ketone is prefixed as a 3-keto, aldehyde is coded as a Al, that is butane Al, 3-keto-butanol. Answer 2 is right. Yes. 10th question. This is IUPAC name of the compound is written in a branch type and all that attached with a isopropyl seems to be, but the longest chain is pent attached with 2 methyls at the second and third carbon. So, therefore, the longest chain pentane with the 2,3 dimethyl pentane is the right name. Next. So, in this also we have a small problem here. From the either side we have 4 carbons, 1 carbon is missing. We have 4 carbon chain, that is butane having the chlorine and the bromine at second and third. From which side numbering means it is here when the 2 plus 3 total is same, we have to follow the alphabetical order for the carbon. So, bromine happens to be the B, starts from first. So, therefore, 2 bromo 2 chloro is the right answer. 2 bromo 3 chloro, 2 bromo 3 chloro is the right answer. Answer goes to the third bit, 4th bit. Next. Yeah. Then we will go to the another small unit called isomerism. This is also a basic principle in the I am the general organic chemistry. Considerably a big number of questions are coming from the isomerism, because here we have a structural isomerism as well as a geometric isomerism, the optic, that is stereochemical isomerism is there. So, therefore, questions are coming more number in the isomerism. So, I will take up a general description in the isomerism. Isomers are the actually isomers should have the same molecular formula, and different properties. At least one property should be different, either physical or chemical, then such two compounds are said isomers. Now, any two compounds which have got some relation, the relation between the two isomers is known as isomerism. So, the isomerism is broadly classified into the two types, structural and the stereoisomerism. Structural means the order will be changed, like when A, B, C, D molecule is there, it can be reconstituted like A, D, B, C, right. So, this type of the reconstituting the atoms jumbling leads to the structural isomerism, whereas a molecule like if A double bond B is there attached with C and D, here E and F is there. So, this is a fixed molecule. By changing the C and D groups, we will get the order will be same, but the isomer will get it. So, A, B is same, E and F also same, but the C is shifted to down and the D is taken up, means we have not changed the order. But what we have changed means positional arrangement we have changed. So, therefore, such a type of isomerism goes to the stereoisomer. In the structural, we have chain isomerism. Whenever the order of the atoms, like when 4 carbons are there, we can arrange in the straight chain or in the branched one. This type of isomerism is known as chain isomerism. When we have the positional isomerism, like whenever there is a functional group, like for example 1 chloropropane with 2 chloropropane, the functional group should be there, otherwise this isomerism won't come. The functional group position on a given chain should change, then the positional isomerism is coming. Then we have a functional isomerism. In the functional isomerism, like a 2 carbons separated with an oxygen is called ether bond, whereas 2 carbons attached with O and a hydrogen, this is an alcohol, this is a ether. So, the molecular formula happens to be same, C2H6O, but one ether and one alcohol happens to be an functional. So, like that aldehydes, ketones, 1 degree amines with 2 degree amines, cyanides, isocyanate, huge number of compounds, but remember the molecular formula should be same. Functional group is different, therefore, we are calling the functional isomerism. Then we have a tautomerism. In the tautomerism, functional group will be there, like for example, ethyl alcohol is there, which can be changed into an aldehyde. So, this is an enol, this is a en with a al, enol, this is a enol. So, enol goes on, changes into that, there is an equilibrium will be there. Equilibrium stands for equal, means same, but what is same means percentage is not the same, but the conversions are A to B, B to C will be same. So, there will be one compound you can't prepare, if you, the moment you prepare the other, it will goes to the, but however, depending upon the thermal stability and all that, sometimes this may be around only the 1.1%, the rest will be the 99.9% will be the aldehydes. Because of the stability of this, one of the isomer may lead. And in the metamerism, we have another type of the observation. Here we have a 3 carbons, for example, a functional group with a ether. One of the carbon you change to that side, keep the functional group as it is. See, both are ethers only, but one carbon changed. So, redistribution of the number of carbons attached, the alkyl groups attached to a functional group, when you change the carbons within them, then the functional group remains the same, but this type of the isomerism is not a chain isomerism, we call it as a metamerism. In the stereoisomerism, once again we have the 3 types. Whenever a double bond is there, the ABCD what I shown is an example come under the geometric type of the isomerism. Whenever there is a single bond is there, the single bond rotates and leads to give the arrangements. If A and A is there same side, if you see from this side A covers the A, but if you rotate A comes from the down, so you may get an anti-configuration and so on. The type of isomerism is called conformational. Whenever carbon has a chiral carbon, or whenever the compound is you cannot cut into the two halves, or the absence of the symmetry elements leads to generate the another compound which is a mirror image of the other compound, and they have a non-superimposable mirror images are going to create a optical isomerism. Okay, this is second one is called conformational, and the third one is going to give a optical isomerism. Now let us see some examples and work out the isomerism questions. Which of the following is a pair of functional isomers? The pair of functional isomers means if one belongs to aldehyde, the other one should be the ketone. In the first example, see, first carbon compound has a 3 carbons, second one 2 carbons, delete it, they are not isomers at all. In the second compound there is an acid, the other one is a ester. So happens to be the number of hydrogens and all that fits, so therefore answer goes to the 2. In the third one we have a propanoic acid and the alcohol one, this is as also reverse is the case actually, these are the identical compounds in fact. And the fourth one is ethanoic acid and aldehyde, one oxygen is different, so this molecular formula won't fit, so the answer goes to the second bit, that is the propanoic acid and the methyl ethanoate are the functional isomers, ester and acid. Next, which of the following columns, the column versus 1 versus 2 you have to assemble. Acetaldehyde and vinyl alcohol are the tautomers, that is goes to the second bit. Eclipsed and staggered ethane goes to the conformational isomerism, and the plus 2 butanol and minus 2 butanol happens to the enantiomers A bit. Methyl N propylamine and diethylamine happens to be metamers here. So the answer 2, that is set of that answers 2 happens to be the correct one. Next, different conformations of the same molecule. Different conformations means the single bond by rotation, what all you get is called conformations. By rotation of sigma bond, what you get is called conformational isomers or conformers. By rotating you are getting, they also have another name called rotamers, therefore answer goes to the 4. Next, which of the following exhibits enantiomerism? Enantiomerism means a carbon which is having a 4 different groups like A, B, C, D. Okay, then this carbon is said to be a chiral carbon which is responsible to create the non-superimposable mirror image. It's, you see the second answer, you see second answer, second carbon, we have hydrogen, bromine, methyl and ethyl. So this carbon is said to be a chiral carbon which is having the 4 different that is non-equal groups are there. At this carbon you cannot cut the compound into 2 halves, therefore such a carbon is called chiral carbon, as a chiral carbon people say, and such a compounds are going to show this optical isomerism or enantiomerism. Next, the 2 enantiomers of secondary butyl chloride differ from each other. Secondary butyl chloride happens to be a 4 carbons are there, the chlorine is at the second carbon, this carbon is a chiral carbon. So this exists in the 2 isomeric, these 2 each other are mirror images and non-superimposable isomers, you are getting this one. They will have the same boiling point, all physical and chemical properties will be same except the optical rotation, that is called the specific optical rotation will be different, that is second is different. Density, see, they are isometric, all bonds will be same level. Next, maleic and fumaric acids. Maleic acid means there is a double bond with 2 carboxylic acids same side is called maleic acid. This nomenclature common name is there. The other one is fumaric acid is a 2 carboxylic acid on the opposite side. These 2 have a common names. Actually one is a cis compound, you have to name it is a but-2-ene dioic acid cis 1, the other one is trans 2-butene dioic acid systematically, but unfortunately we have a name nomenclature which is also crept into the people of the scientists. Even common names are more popularly we are using. The one is a malic acid, means same side, opposite one is called a fumaric acid. What is the relation? They are just the groups are exchanged. So, in the whenever the double bond groups are exchanged, the compound is a different one. They are not superimposable, they are not mirror images, they are totally different compounds which have got a, because of the double bond we cannot rotate, they are not conformational isomers. So, such isomers are, we are saying, geometric isomers. In one way they are also called diastereomers also in another type of classification. Next. There is an ether containing methyl and propyl, another ether again methyl and propyl, but this propyl is a N-propyl, the other propyl is a isopropyl. You may say methyl N-propyl ether, methyl isopropyl ether. It looks like a chain isomerism because there is an isopropyl, but actually the methoxy group is on the first carbon of the propane. In the second one, methoxy group is in the second carbon of the propane. So, therefore, first carbon, second carbon means position is changed, therefore, positional isomers. Next. Functional isomer of 2-butene, actually this is the spelling mistake is there, butene, 2-butene. 2-butene means there is a double bond. So, the first option is a 1-butene. These two are positional actually, but there is another 2-butene is there which is a cis type and a trans, that is has no meaning actually. The answer is a third answer, that is a cyclobutane. It is actually cyclobutane. In the cyclobutane is a functional group is the alkane, and whereas in the butene alkene. So, these two are functional groups are different, therefore, functional isomerism is the right answer. Ethyl chloride and ethyl bromide are, ethyl chloride and ethyl bromide are what type of isomers he is asking. This is a somewhat misleading question once again. In one compound we have a chlorine, in the other compound we have a bromine. So, they have no relation, that is same molecular formula is not that is fulfilled. So, therefore, they are not at all isomers. So, fourth option is the right answer. We think it is a functional isomerism because chlorine, bromine functional isomers, but it is not isomers. Next. Tautomers will be in the equilibrium, which means their percentage is equal. That is wrong. Per unit time, equal number of conversions, A to B, B to A goes on changes. That is why whatever the percentage you take, after several hours you come and see, that will be percentage same, but they go on change. That is why it is called dynamic equilibrium. There is a dynamic equilibrium existing. However, by changing the temperature or by changing the acid medium and all that, these percentages we can change, but after some time once again a new percentages will come and they exist in the equilibrium. Next. This is in this compound shown R configuration at second carbon, if this the condition is mentioned. However, it is really R also, but even then if this compound shown R configuration is second carbon, at third carbon configuration is expected to be. So, the first carbon and see verify the third carbon, second and third carbon they are mirror images. So, at the first carbon we have a R, second carbon happens to be, if it is a mirror image it will be S actually. Is it so? If the first compound is R, its mirror image is S. So, therefore, the answer is S configuration actually. It is answer goes to the 2 actually. The answer is mentioned 4, but it is S. It is R and S are the mirror images there. Next. Regarding the 2-butene, which isomer show the higher dipole moment? In the 2-butene can exist in the E as well as Z. E means opposite to methyls, Z means same side. Same side, whenever the methyl is there, dipole moment will be high because there is no compensation taking, they are on the same side. So, opposite side they push. So, because of the plus I effect there will be a cis compound or Z compound will have the higher dipole. Answer goes to the 2 therefore. With reference to the CIP rules, among the following the group with the first priority. So, in the RS nomenclature, the basis for this C1 is first all the 4 groups. I will give some certain points on this particular nomenclature. A compound like this, for example, if an aldehyde is there and a OH is there, a CH2OH, this is known as glyceraldehyde. Okay. So, we have a relative nomenclature, but we have a RS nomenclature for this one, which is based on this CIP rules. CIP stands for the Kahn, Ingold and Prelog rules. So, in the next question we have that also. According to these rules, all these 4 groups are going to be given a priority number. So, here this OH is given 1. Why it is given means the group which is having the atomic weight 16 is given a first preference. Here carbon is 12, this is having again 12, this is having 1. So, therefore, the first atom oxygen 16 is given preference 1. Regarding the second preference is both are carbons 12 12. Here the double bond O is there, single bond O is there. So, that is 16 oxygen is doubly attached, therefore, it is 2. So, this is 3, this is 4. So, first we have to give the, according to the based on the CIP, all the groups should be given a priority numbers. This is the rule 1. After the rule 1, we have to bring the 4th group to the down by having a exchanges, side exchanges only allowed, not the opposite. Why 2 means if I exchange 1, the original compound R will become S. So, therefore, in order to retain the same old, we are doing in fact 2 mistakes. So, this 4 comes here, 3 goes there, and 2 comes here, 1 goes there. Now, the symmetry of this molecule is actually the 2 and 3 are bent towards you and 1 and 4 are going backside, right. Now, if the other 2 groups are going backside, you are holding this and shifting the 3 groups towards you and reading the 1, 2, 3, making into a circle. So, if 1, 2, 3 are like this, 4th group, think that it is not there in the figure, read 1, 2, 3. It goes to the clockwise direction, therefore, it is given R. If anti-clockwise direction comes, it is S. So, therefore, this glyceraldehyde is given a R configuration, right. If the OH is perhaps this side, it will come S configuration. That means, its mirror image happens to be the S1. So, the R and S nomenclature is basically given by the to show the it is an absolute configuration, wherein you need not to have any reference with another compound. It is a single compound, provided the compound should be symmetry should be very clearly mentioned. This model is called Fisher model, need not to be Fisher model in any other model, but the compound symmetry should be clearly mentioned. In the Fisher model, 2 groups which are horizontal are projected towards you, 2 which are vertical are shown backside. So, this is the molecule. So, here 2 and 3 are towards you, 1 and 4, this is making 109, this is making 109. Now, we have given a rules and we brought the 4th group, that is least preference group is brought down, and you are bending the molecule, you are reading from the rear side of the 4th group, making 1, 2, 3 into the circle. If the circle goes to the clockwise, it is called R. If the circle goes to the anti-clockwise, it is called S. This is called RS nomenclature. Next, so therefore, here only the priority is asked. So, the third one has a C double bond O. Naturally, double bond O means all are carbons only. So, the third bit we have a double bond O means second preference based on the second atomic number. We have fixed that the third is the most preferable one. Next, which one of the following of 2,3-butane diol is enantiomeric? So, 2,3-butane diol can be two OHs can be like this, or it can be one that side, one this side. If this is the case, we have a one more mirror image also. Now, here if this is R, okay, so this happens to be, it's a mirror image of this one. So, therefore, yes. So, there is a compensation is taking place, net optical activity will be 0, such a compounds are called meso. Okay. That means RS butane diol is a meso compound, right. So, if this is R, so this is not a mirror image. So, therefore, this is also happens to be R. Okay, this is RR, and this is a mirror image of this one, so it is S. Okay, so it's not mirror image, therefore it is R. So S and R, 2S, 3R. This is 2R, 3R. 2R, 3R is optically active. If it is, I take as a plus 1, this is a minus 1. So the question, see here, 2R, 3R, R and R, and S and S. The other one will be SR. This is R, RR, and it's not mirror image, so therefore yes. RR and SS are the active. This is also yes, I am sorry. So 2R, 3R, 2S, 3S is an active one, whereas R and S are S and R are meso compound. So therefore the answer goes to the first one, that is 2R, 3R and 2S, 3S is an optically active. It has got the both are the enantiomeric to each other. 2R, 3R and 2S, 3S is the enantiomeric pair, and the 2R, this is 2R and the 3S R, and 2S, 2R and the this is R, 2R, 3S R, 2S, 3R. Both are nothing but the same compounds, and it is exists as a meso whose optical activity is 0. Next, which one of the following compounds has a Z configuration? The Z configuration means this is also something like the RS configuration, which is a latest nomenclature in the optical isomerism. Like that, we have a EZ configuration. Previously, we used to have a cis trans nomenclature. If the two methyls are this side, we used to say cis compound. If the two methyls are opposite, we used to say it is a trans compound, right? This is the old nomenclature. Now, instead of the cis trans, we have a latest configuration in which also here the hydrogen and the methyl. So according to EZ nomenclature, we have to allocate the numbers for these two groups. This is number 1 group, this is number 2, based on once again CIP rules. What are the CIP rules? The CIP rules called Kahn-Ingold paralog. Both all are the three different scientists who are a Nobel Prize winners. They have introduced a method where this priority giving they have given. So this is first preference, second preference. This is again first preference, second preference, hydrogen. So preference 1 goes to the same side means Z. Z stands for the Zusammen. Okay, Z means Zusammen. What is Z here? What is Zusammen? Two most preference groups are same side, therefore it goes to Z. If the groups are opposite, like a trans compound, this is the preference 1 and preference 1 is opposite, therefore it is E. E stands for the Entgegen. Entgegen means opposite one. What are opposite? Two preferable groups are in opposite. See here, number 1, chlorine, bromine are the number 1 groups are same side, therefore it is Z compound. In the number 3, chlorine and the bromine, isn't it? Top side chlorine and bottom side bromine opposite. So 1 and 1 opposite, that is the E compound. So the answer goes to then the third one. In the third one, left side bromine is the preference 1, right side methyl is the preference. So bromine methyl is same side, again it is a Z compound. So 1 and 3 are Z. So here it is Z configuration is asked, therefore 1 and 3 answer means fourth bit is the right answer. Right. Next. According to the Kahn-Ingold paralog sequence rules, the correct order of priority for the given groups is, see here, the first and second COOH groups are there. In the third and fourth OH groups, that is starting with oxygen. Oxygen is the highest preference, that is 16 atomic weight. So the most higher atomic weight will be kept on the first. So the answer is between the third and fourth, because 2 OHs. Next you come. Next CH2OH is there, COOH. COOH means CH2OH means 1 oxygen. First element is carbon. Second element oxygen. Here second element is double bond O and another O is also there. So therefore COOH happens to be the second one. Then goes to the aldehyde. Then goes to the CH2OH. So therefore the last rule, that is the last order, that is the fourth bit is the right answer. Next. That's all. So here the EZ and as well as the RS configuration both are latest nomenclature. However, they have basically dependent on this CIP rules. So, once we know this about the acquainted about the what are CIP rules, then implement to that to identify RS configuration as well as the EZ configuration. Thank you.